The good news, my recording for software is finally actually working now. Bad news, I am feeling a little sick, so if you do hear me coughing or sneezing or a little bit during this video, my apologies. Good news is we're on section 1.5 on projectile motion. And recall from grade 9, not grade 9, my apologies, that is the force of habit. Recall from grade 10 that, for some reason my picture is not moving now, there it goes I believe, from grade 11 that a projectile is any object in which gravity is acting on. And gravity is the only force acting on it. Let us just suppose in this case that we're going to take an ordinary object like, well, since summer's coming up, let's say a soccer ball. I can't even remember what a soccer ball looks like. I remember it has little octagon shapes on it. We're going to kick it into the air at some angle theta and some initial velocity v. If it is kicked at some initial velocity v, we do know that that velocity can be broken up into its x component and into its y component. And a projectile will follow a parabolic trajectory. And at each point during its trajectory, we could definitely break up, sorry, that should say y over here, our velocity into separate x and y components. Now do recall that at the top of the path is where our height is at its maximum. And at this part, our initial velocity for just a mere moment in the y direction is 0, while in the x direction it stays constant at vx. So velocity in the x direction is uniform. And our velocity in the y direction is non-uniform. And that is because we have the acceleration due to gravity of 9.81 meters per second down towards the Earth. And it should be noted that while we look at this trajectory, at the very initial beginning, your vertical velocity is at its greatest. As we get more and more into the trajectory, the velocity, and that's the vertical velocity, will decrease until we hit the highest point and hit 0. And once the vertical velocity hits its highest point, that is when the projectile begins to fall downwards. You will notice in this case that our soccer ball is being kicked and it's beginning and landing in exactly the same height. When this occurs, when our projectile lands in the same spot, we can use our range equation which tells us that our displacement in the x direction is simply our initial velocity over the acceleration due to gravity sine 2 theta. Meanwhile, our height, this will be our land and begins in the same spot, as our initial velocity vi sine theta squared all over 2 times our acceleration due to gravity. And furthermore, when we have this occur in the same spot, landing and beginning in the same height, our time can be easily calculated using 2 vi sine theta all over the acceleration from gravity. So let us actually look at an example of this. And here's our problem that we have. I'll let you read it before I do continue. Right there, that is a scribble. I accidentally wrote an A instead of a G, just in case you're wondering what it was. So a soccer player who kicks a ball from the ground, initial velocity of 15 meters per second. Ball is kicked at an angle of 20 degrees above the horizontal, and we are going to be looking for the time of flight and the horizontal distance that it actually traveled. So this tells us that we have our soccer ball, similar to our just generic discussion at the very beginning. It's kicked at an initial velocity of 15 meters per second at an angle of 20 degrees. And because we can break that up into both the x component and the y component, in a few seconds we'll see why we will do that. So we are asked in part A to determine the time of flight. We take that because we have the same landing height as the initial height. We could take our range equations, and this will tell us that delta t is 2 vi sine theta all over the acceleration due to gravity. And a simple substitution gets us and use of our calculators as well, gets us that our time is 1.0459. I look at my initial question. I see that my velocity was 15 meters per second, so the 2 significant digits. Therefore, time of flight is 1.0 seconds. And we can determine our horizontal distance very similarly. Same landing height as our initial height. So I know that my initial speed, again, 15 meters per second. My acceleration due to gravity, 9.81 meters per second squared. And theta is 20 degrees. So my displacement in the x direction vi over acceleration due to gravity sine 2 theta, and that will be 15, I forgot my squared, sorry, 15 squared over 9.81 multiplied by sine 40 degrees. So that will be 14.7428, and therefore the horizontal distance that the ball travels is 15 meters. Well, that's nice when we have a ball landing at the same height that it was initially started at. What happens, however, if that doesn't occur? So what happens if, say, looks like I lost my screen, or my computer just went into sleep mode for 2 seconds, a golf ball launched from the roof of a school with a velocity of 20 meters per second, an angle of 30 degrees above the horizontal. If the roof is 40 meters above the ground, let's calculate a few things. So let us start by declaring that up and to the right will be positive. If I have the school looking as follows, the ground, golf ball at the very top, it's being launched at an angle of 30 degrees above the horizontal with an initial speed VI of 20 meters per second. We have acceleration of gravity acting down, and my displacement negative 40 meters as well because we were going in a downward direction. So for the time of flight, there's two different portions that we have to take into consideration. We know that the golf ball is going to rise to its highest height, and then it's going to, and right there our V at that height will be 0 meters per second, and then we're going to have a portion where it falls. So two parts to this answer. We have a rise when it goes to its maximum height, and then we have when it's in the fall. And we must use both of those to calculate how long this will actually take. So let us begin by looking at the rise portion. It should be reminded that when we're calculating our initial velocity in the y direction, that will be similar to our displacement. It will be VI sine theta, so 20 sine theta. So my initial velocity in the y direction when we punch that into a calculator is 10 meters per second. Our acceleration due to gravity, negative 9.81 meters per second. And I think about the rise. It's going to start at the school building and it's going to reach its maximum height when my initial velocity, or my velocity, is 0 meters per second. So that's the ending part of my rise. What we are going to do is calculate our time, and we will calculate our displacement in the y direction. And to calculate our time, we'll use our kinematic equations. Easy one here. Since I have that my final velocity is 0, I can rearrange, and that will give me that negative v in the y direction is my acceleration and time. Divide both sides by my acceleration due to gravity, and I actually end up getting that my time will be v y over my acceleration due to gravity. That should be a positive, sorry for putting a negative there. So, therefore, substitution. My time is simply going to be negative 10 over negative 9.81, which gets us 1.0204. You will notice that I've included a few extra decimal places. This is for accuracy before I look at my significant digits at the very end. During our rise, if I look back at my diagram, it's going to increase a certain amount. There will be a certain amount that it will increase from my initial height of 40 meters that was given. So I should actually determine that amount quickly right now. Using the fact that Vf squared is equal to VI squared plus 2AD. Similarly as before, VF is 0, so I have negative VI squared, and if I do some quick manipulations, that will tell me that that will be divided by 2AG, and that will be my total displacement. So negative 10 squared all over 2 times negative 9.81 is my displacement in that y direction, which we should calculate quickly. And give you 2 seconds to get caught up. If we were to divide these two, I realize I did not have my correct answer when I initially did this. That's why you hear me punching my calculator right now. That displacement is 5.0968 meters. That was added on to that height from the golf ball. And we need to use this for the next portion. Because the next part of our motion here is the fall. So that was the rise portion. We're still on part A. We look at the fall now. And during that fall, I notice that at the very beginning of this motion, my initial velocity in the y direction will be 0 meters per second. My acceleration due to gravity is still negative 9.81 meters per second. My displacement in the y direction, it was initially at 40 meters per second, and add this 5.0968. So it will now be negative 45.0968 meters, and let's calculate our time. So that will be kinematic equations yet again. My displacement in the y direction will be equal to that plus 1/2 AT squared. That's acceleration due to gravity again. My initial velocity, because we're at the top of the flight, is 0. So my displacement in the y direction is 1/2 AT squared. And rearranging this, I would multiply by 2 because of my fraction on the bottom. Divide by acceleration due to gravity. That's gotten rid of, and I need square root. So time is the square root of t delta dy all over my acceleration due to gravity. And that will be 2 times negative 45.0968 all over negative 9.81. My apologies, I'm noticing to myself I'm speeding up now. I'll slow down just a little bit, but let us calculate this now. If I take 2 times negative 45.0968, I'll divide that by negative 9.81 and square root. You get the time during the fall portion is 3.0321. So it took 3 seconds to fall and 1 second to rise. So my total time will be the 1.0204 add 3.0321 together, and you get 4.2212, 2 significant digits. Therefore, time of flight is 4.2 seconds. And then part B, the horizontal distance traveled. While my initial velocity in the x direction, which remains constant, will be 20 cos 30 degrees. We calculate that. To be 17.3205. My time is 4.2212 seconds. Our displacement in the x direction will be Vix multiplied by delta t due to uniform motion. So that will be 17.3205, and that will be multiplied by 4.2212. Notice I went back to my more accurate answer, and we get that the horizontal distance will be 73.1133. So therefore, our horizontal displacement is 73 meters from the school. And there are the two examples. Second one, a nice example, a long example, but it really shows a lot of the projectile motion problems that you will see.